Hello there, UILCS coders, and in this video we're going to cover the tree map data structure in Java. So before you watch this video, watch the red and black, the red black tree video, right? Because tree maps are underlyingly backed by a red black tree, but you don't really have to know how to code a red black tree. I code it in the video. I'm not going to code a tree map because you don't need to know how to code one. You just need to know how it works. Okay, let's start talking about it though. Enough. Yeah, let's start talking about it. So what is a tree map? Hopefully you've seen the red black tree video if you're here. Well, a tree map is a map that follows natural order. So how does that work? Well, I have this red black tree. Yeah, I said that correctly, right? I have this red black tree here. And pretty much, as you know, with any binary search tree or any binary search tree, the left child is less than the parent, the right child is greater than the parent. So it just follows that normal BST property, right? We're just checking if it's lexicographically, we're comparing it to here lexicographically, right? So we use compare to. So it'd be like compare to A dot compare to B. And we said if this returns a positive number, then A is bigger than B. So that means it should be right child. If this returns a negative number, I'm just using 1 here. A is less than B, so B is so that means that B or A is the left child. And I'm just saying that A is the inserted, so I'll say inserted, and I'll say B is our parent. I don't say parent, maybe a better word is current. So it's the current node we're looking at. So that's how we maintain natural order. And then when you're, obviously if you follow BST, we know that in order traversal gives you the tree in sorted order, right? So there you go. That's how we get our elements back to us in sorted order. For performing in order traversal on the tree we make, we use in order, we use a red black tree. Sometimes in my mind I try and call it, I try to call it black red tree. It's stupid, it's a red black tree. I guess both the same thing, I guess. But I lost my train of thought completely. Okay. In ordered is sorted order, and we're using a red black tree because remember binary search trees have that limitation where it's not always balanced. And red black trees are pretty fast. I'm pretty sure they're faster than AVL trees, which is why we use them. Don't quote me on that though, because I don't know. But that's enough on the technical side of things and how it works technically. It's just a tree. That's about it. So there's much more you need to know about that technically. Let's keep this like close. So now let's start jumping right into the methods. So what are some important methods? Well, you know of the put, the compute. It has all of the map methods, right? So I'm not going to go over them again, but it has its own methods too. So let's discuss ceiling, floor, upper, and lower. If I were to say ceiling of 2.5, ceiling of 2.5, for this array of numbers, or array is fine. What is numbers? What would that mean? So we'd go here at 2.5. 2.5 would be here, right? The ceiling is basically saying, okay, it would return the next greatest number. So it would return 3. It's essentially, if you looked at mat.ceil, that's not how you spell it. It's like this. Of 2.5, what does that give you? That gives you 3, right? So you can kind of view it, and then in terms of this array, if you're doing 2.5, it gives you the in order successor of 2.5. It was in the array, which would be 3. This is the next biggest value. In order successor is just fancy terminology. But this is where the concept derives from. Then, you might be wondering, well, Sid, what if I did 2? what does math.ceil of 2 return? 2, right? So if I did ceiling of 2, so if I just erase all this stuff, it wouldn't like go and be like, okay, a 2 will return 3. No, it would return 2. So if the element doesn't exist, like if it did 2.1, 2.1, it's not real, it doesn't exist. Let's return the next highest up, which would be 3. Or you could also look at it as just doing math dot. Well, you can't really look at it like that. It's from that same principle, but look at it like essentially if the element exists, return that element. And if the element doesn't exist, return the one that would be like it has 1 greater than it in the position, right? 2.1, the next one that's greater is 3. That's ceiling. So floor is the same idea, right? Mat.floor. The floor of 2, it returned 2. If it did floor of 1.2, it returned 1. Same idea. If it's in the array, return it. Otherwise, let's say like 1.2 would be here, I guess, ish. Find the element that's in the array that would come one before it, which is 1, and return that. The upper and lower are similar but different. If I did upper of 2, it'll return 3. Okay, so upper of 2 will always return the one greater than. So for 2 it would return 3, for 2.5 it also return 3, right? For both of the instances we talked about, it basically just no matter what the case returns the element 1 greater than the one you passed in. Ceiling had that limitation where it was like if the element you passed in was in our array, return that. Otherwise return the one greater. So if because 2 is in our array, if we pass 2, you'd get 2. Otherwise return 1 greater, like if I did 2.5, that's not in our array. We do the element 1 greater than 2.5 that's in our array, which would be, I wouldn't say 1 greater, sorry, I'd say like the element that would come after 2.5. So 2.5 was here, comes after 3. In order successor is also used as a terminology for that. And then the same idea with lower. So lower is like floor only, but if I did floor of 2, I'd get 1. So floor of 2 would give me 1. So that is lower, ceiling, floor, and upper explained. So why I'm explaining that, that's very important when it comes to these methods. So because we have a tree map that's not a hash map or it's not any of the hashes, we actually can return some data about like our elements to our user, right? So with the hash map, everything was weird. It was in this random, it was in the hash table, right? It wasn't that easy to say if I want like a subset from like 1 to 4, sub map from 1 to 4, these elements, give me them. That's not that easy. In a tree map, it is because we were mapped with a red-black tree. So the first method I want to discuss is the ceiling entry. So we'll talk about ceiling entry. So ceiling entry is the first method that we will be discussing. Ceiling entry returns a map. Back to the description room. A map. That's a horrid writing. Map dot entry key comma value. Right, it returns an entry. That's nothing new. Don't be scared by the generics, you know what that does. Ceiling entry, so we're gonna pass in a key. So if you remember with the arrays, what did I say? It's like the same idea, right? If we're passing in a key that exists, return the entry at that key, otherwise return the next greatest entry. That is what this method does. And conversely, so I'm not going to write that out because we just had that whole section explaining ceiling, floor, upper, lower. There is ceiling, key. Excuse me, that takes in a key and then returns a key. So it's basically the same idea, right? If the key exists, return it. Otherwise, return the in-order successor. Now, just as there is sealing key and sealing entry, we can say that there is a, copy this. Did I get it? How did I not get it, bro? I like that I got it, bro. Yeah, it's a little bit big. Let's shrink it down a bit. Take this. Why am I opening up snipping tool? That's actually not what I need to do. Copying this, copying this, and pasting this down. Okay, so just as there is sealing entry and sealing key, then there's also a floor key entry and a floor key. And then there's also, paste it down here, get rid of this portion of it, a higher, okay, I'll write that, it's a higher entry and a higher key, and then there's also a lower entry and a lower key. So there's a lower entry and a lower key. I have seen them test on this before. The lowers, so make lower. Well, they're in their right to test on this because it's a part of collections, right? Okay, so those are some big ones we just covered there. We covered a lot of this list just simply like that. There are some more we do need to talk about though. There is a type of map, we call it a navigable map. Okay, comma V. So this is a method, it's called descending map. And it's pretty self-explanatory what it does, but I'll write it out anyways. A descending map returns, let's say, reverse order of map. Is a good way for me to describe it. So return the reverse order of the map. So what does that mean? In the red black tree, instead of going in order sort, you would go, I don't know if there's a sort that's opposite, but it'd mostly be like this, this, this. And then you would do this, then this. Or let's see, it'll be this one, then this one, then this one, then this one. Then you would need to go to this one, then this one, then this one. Right, but that's irrelevant. It's just reversing the, that's just one complete reversal. Right, but it just reverses the reverse order of the map. If the map is in sorted order, reverse that, that's what that does. And then conversely, there is a let me guess the portion for you to see. Where there is a navigable set. I'll replace where I've written map and I'll replace it with the word set. Navigable set. So it'll return a descent reverse order of the not map, but the entries. Okay, so just as how there is a reverse descending map, there also exists a descending key set. And I think it's in the name what it does, and it's of course navigable set. It's not really, of course, we don't cover the navigable map and navigable set in this. Is it like I don't know how else you'd say it. It'll return reverse order of key set. And key set is from maps. It's just the set of your keys. Or if you're on a hash set, a map, that's your hash set. So that is covering all of this. Let us cover the next method, which is map dot entry key comma value first entry, which returns head entry. But then, right, you're seeing that there's a lot of repetition of ideas in this, right? If there's head, if there's first entry, I'll just copy this section. This first entry, there's also a last entry. And what's that? That's the tail. And then you have key. You have first key, which is the key of the head entry. And then you have tail key, which is the tail of the head the key of the tail entry. These are all O1 by the way, because so let's assume you have a reference to your first and last elements. Make sure I'm doing everything correctly. Yeah, sorry. This shouldn't be tail key, this should be last key. Oops. Used to follow the convention first last. So there's also the idea of there's a few more. There's map dot entry key comma value, and this next one is pull first entry. So it just will give you the first entry and remove it from the map. So in that case, that'd be cool, right? You get to, if you want to go through that with this black tree, you can. We can even go through that. And no, we're not going to go through this video because I don't want to go for the black tree stuff in this non-red black tree video. But that'd be cool, right? You're going to do remove on a red black tree, which is always interesting. And then, of course, if there's a pull first entry, there's a pull last entry. Pull last entry. So these final bunch of stuff is just more of the navigable stuff. So there's a method that's called navigable key set. Is it navigable? No. It's called it's navigate. So, navigable key set, which will take in will give you a navigable set. I guess K. I've been writing K comma V. And why did I write K comma V here? It's literally the key set. I forgot to change that. Sorry guys, if that confused anybody. It's just K because it's a. This one is just going to be a normal key set. Key set. Come on, Sid, you can make better than that. It's just a normal key set. Nothing special about it. Alright, let's flip over now. The last methods are cool. We have sub map, And there's two forms of submap. So there's submap where you just pass in your from key and your to key. And then there's a submap where you pass in your from key, a check, a to key, and another check. So first off, what does submap do? It'll take a portion of your map and return that. So from to, it'll be a view, I'm pretty sure. So any edits you make to this will be reflected on your map and vice versa. Okay, so or I don't know what the vice versa part, but that's know any edits you make on submap will result in changes in your actual map. So it just gets the map from this range, this index. Now the checks determine, do we want it to be this? Like what do we want do we want to include or not include the elements at from and at to, right? So if your first check is, whenever your check is true, that means yes, be included, otherwise it's false. So if this was true and this was true, my submap might look something like this, from to, and the brackets indicate that we include the element at from and at to. Now you might notice I said you haven't wrote any return types. This should be the same though, right? No. So the way I like to look at it is the more simple one is sorted, right? The S in sorted, simple, that's a sorted map. I need to put generics on that, so I need to back up a little bit. Okay, comma V. Right, and then you can say the more confident or complicated one is the navigatable, or no, it's just navigable map. K, comma V. Sorry that my handwriting's a little bit bad, but I think it's fine. You understand where I'm getting at, right? Even if this V looks atrocious. And then there's one more. So this is where I got mixed up with. There's lastly the idea of the tail map. So it's a little bit confusing. So the tail map, it only takes in one parameter, which is just one key, or you have the version where it's that key, and then it's so key, and then you have your check, your boolean, your check here. So then what is this one then? It must be a sorted map because it's more simple in the parameters, and we said the sorted one is more simpler. KV, and this one must be a navigable map. K, comma, V. So tail map will return everything from that key to the tail. So it'll be a submap from key all the way to the end. Navigable map is like, hey, do I want to include the key or not? You'll always go up to and including the tail. Pretty much everything that's greater than your key value is always a part of this tail map. But you can just use check, so if check is true, it'll look like this, brackets, key, tail. If check is false, well, check is false, just look like this example down here, right? So the check only modifies this one, makes your key inclusive or not. You're always including the element at the tail. And that is the sorted map. There's nothing else I need to cover. The methods aren't too bad, to be honest. Of course, you have all of your map methods like compute, merge, put, remove, get, all of that. Of course, you also have your collections methods. So you have a lot more methods that you can do from a tree map than just these, but these are the tree map specifics. You'll notice a lot of them are very repetitive. First and last is a bunch of there's like four methods talking about the first and last of things. Six methods talking about the first and last of things. There's what, eight methods, and they're just if you know ceiling, floor, higher, lower, you're good. Other methods like ascending map, ascending key set are pretty self-explanatory, and they probably won't show you that. I don't think maybe. Navigable map is also pretty self-explanatory. It's just a navigable key set is also pretty self-explanatory. It's just a key set. Okay, yeah. And of course, submap is in the name, but also if they ask the differences here, oh, oops. If they ask this, I don't know, I don't think they'll ask, but they might. If they ask, the more simple one is sorted, the more complicated one is navigable map, and you also know what these checks mean. And yeah, those are it. Those are the methods. This is the tree map in Java. And at the end of the day, you need one major thing to take away this line. A tree map is a map that follows natural